data and model averaging in RHadoop. And so just to set this up, in medical school, anytime there was teaching or didactics or anytime we were having a discussion, everything really started around presenting a case study. There was a patient with this, and then the whole discussion started. So I want to start that way with a problem that I faced. And so the problem was, if you're trying to predict survival of inpatients upon admission, how do you go about doing that? And in a large healthcare system, you could be looking at thousands of inpatients a month, and if you're using admission lives, you could be looking at millions of data points that you're going to have to train and validate. So as soon as you approach this problem in healthcare today, it becomes a big data problem. And I was facing this scenario. So why would you want to do this? Why would you want to do some kind of scoring for patients, regardless of what you're scoring or what kind of diseases or conditions you're scoring? Well, there's a really long history in healthcare of scoring people. We've been doing it for probably 30 or 40 years. Somebody will make a score for heart disease, and then next year another person will make a different score. And so you've got tons of scores ranging from heart disease to liver failure to trauma and critical illness is probably the field where there's the most scores. And basically these scores are just telling you how sick is this patient. And sometimes they'll build mechanisms and algorithms around the score where you say, if you reach this score, then do this. But they lack confidence in these scores, and in reality, they're just not really used, which is kind of ironic considering there's so much literature about different scores in medicine. So, why are we creating a new score if nobody uses it? Why would you want to do that? Well, we have all these existing scores, but the reason they're not used is that, yes, they're well validated in the literature, but their sensitivity, their specificity, the discrimination, it can be pretty poor. And the reason behind that is, you might have developed a clinical score up in Canada on a set of 400 patients, and it worked really well for that population. But then when you move that down to, let's say, a massive hospital in Florida, how well is it going to generalize? Or, you develop it on a pretty homogeneous population, and then you move it to a very heterogeneous population. It's really hard to get these scores to generalize well to other populations, even when they're well validated in the literature. And I think this cartoon kind of sums up another aspect of the problem with clinical scoring. When you developed a score 30 years ago, you didn't have tablets, you didn't have cell phones, you didn't have laptops at the bedside. So you had to make scores that were very easy to calculate and tabulate in your head when you're at the bedside if you're a clinician. And so, the scores with the most clinical utility that were most useful were things that had very low model complexity, but they also had low performance. Things that maybe were, you did a high dimensional regression and had a really complicated score that you created 30 years ago. All right, nobody's going to use it at the bedside because they're not going to add up in some 100 variables in their head. Things have changed today, where now we have mobile at the bedside, we've got data warehousing, we've got very mature IT ecosystems in healthcare. So now it's obvious, the most clinically useful things are the things with a high performance, and typically they're going to be the more complex models. So now we're at this point where we can start shifting from scores that are very simple, have very simple frameworks, to scores that are using advanced analytics and machine learning. Now, even though a lot of people understand that we're at this place where we can have these complex scores that have a lot of utility, there are cultural problems around this. So try and tell a clinician that you just created a black box score that you validated against a score that's already in the literature. Try telling them they can take that out and then use it today with their patients, and you're going to get a lot of pushback. Even if you show them that you can do as well as or better than their old validated scores. So there's some cultural problems to overcome, but let's all assume today, for the purposes of this talk, that most clinically useful things today are the highly complex models with good performance. Okay, so the problem I presented about the score we wanted to create. Let's take a step back and look at data science from a broader perspective. I think we're all familiar with the problem in data science where we exist in this continuum of either being more of a statistician or being more of an engineer or architect. And we fall somewhere in this continuum. And depending on, if we're more of a statistician, maybe we're going to run into problems on the engineering architecture side with the things we're trying to solve. If we're more of an engineering architect, we're going to have trouble with the statistical problems that arise in data science. And you run into resource problems. So if you're on this engineering architecture side, how do you fill those statistical resource gaps? You go out and hire people. You spend a lot of money on out-of-the-box analytics software that can be very expensive. So living in this continuum is really exciting, but it presents challenges when you're more to the left or the right. And I would say organizationally, when we were trying to create a clinical score, maybe we were more on the engineering savvy side. And so if you're trying to break down, distribute algorithms for this clinical scoring, organizationally, I think that was a challenge that I had. So creating a clinical score using advanced analytics, there's two problems we had to face. How do we distribute the computing? And then how do we distribute the analytics within that environment that we set up? Like I said, we were stronger on the engineering architecture side, so that wasn't really an issue. We can set up an RHadoop cluster in the cloud, and we're ready to go. But then, I wanted to use a linear regression, like a lasso regression, to build this clinical score. And so how do you, we had to distribute those analytics in a mapper and reducer functions. How do you do that with a high-dimensional regression? That's really difficult. Revolution Analytics is a company that will provide some out-of-the-box distribution for these algorithms. They have a product called Scalar, but it's really expensive. You could also go out and hire some statistics PhD that just came out of school, but again, if you're trying to develop a minimum viable product, there's a cost barrier. And if you're not even sure this is a long-term product you want to use and push, then you go out and hire new people just for this project. So this was the solution space I was looking at, trying to fill in this mapping part and reducing part in an RHadoop framework. This was where I was comfortable working because I had a lot of R scripts that I knew worked well and that I was comfortable with. So I wanted to stay in this RHadoop space with my mapping and reducing functions. So the first option was, okay, why don't I just use an ordinary least squares regression? There's a lot of ready-to-go recipes online for how to break that up. But the problem is, I am going to have like 1,000, 2,000, 10,000 input variables when you think about all the possible labs that a patient might get. And so OLS isn't really going to work in that scenario when you're in a high-dimensional space. What's behind door number two? Okay, well, let's say I want to do lasso regression. How do you split that up between the mapping and reducing functions? There are some resources out there that facilitate this, but they're hardly straightforward, and unless you're a really seasoned statistician, this is very challenging. And so, am I going to stop everything I'm doing for 2 weeks and figure out how to distribute this when I'm just trying to design an MVP? It might not be the smartest way to go. So what's behind door number three? Okay, well, is there some kind of resampling we could do where we iteratively do a lasso regression on smaller chunks of our data, and then in the reducing part, we recombine those and average our coefficients to have a master model? So this is what I started thinking about. This is what I started thinking about, and I wanted to start looking into this, and I bounced this off Bob a number of times, and he encouraged me to look into it and think about it. And so what came of that? Let's take a step back and talk about bootstrapping. If you remember, bootstrapping is where, let's say we're doing a study on height, and we measured 100 people's height. Then we can take that sample of 100 heights and resample it 100 times. And then we can do that another 1,000 or 2,000 times. So we're going to get 1,000 or 2,000 means from these bootstrap samples we took from our original sample. And the idea behind this is that the bootstrap samples, the parameterization around the bootstrap samples and the distribution in our bootstrap samples is going to be analogous to the sample distribution parameters, which in turn is analogous to the population distribution parameters. And so bootstrapping is really helpful when we're doing inference with the population that we're either uncomfortable or don't want to make distributional assumptions about. Okay, so why the heck am I talking about bootstrapping when I've got a regression problem? Well, it turns out it works. There's a nice way you can exploit bootstrapping when you're doing a regression. Let's say you have you do a study on height, and you have your 100 heights represented by your y variable here, and then you have x number of regressor variables. So you have a set of 100 of each of those, and you can sample 100 times and build your regression over and over and over. And then the coefficients you're getting out of each of those bootstrap regressions, you can recombine and average. So it seems like the perfect scenario for us here. If we got 20 million samples, let's take 100,000 of them, build the lasso regression, and do that 1,000, 2,000 times, and then in the reducing function, let's recombine it and calculate the coefficients for our master score. So what happened? I took a set of 20 million samples. It was just enough where I could run that with enough RAM, and my scripts are not going to stall or break. So I ran that. I calculated a model, got my coefficients, and then I took 500 times, I took 100,000 samples for my original sample set, and I built smaller lasso regressions, and then all the coefficients I got out of those iterations, I recombined and averaged. And without showing a bunch of results and data, just doing 500 iterations, there was some very nice approximation to the coefficients from the large regression. And as you would guess, these coefficient distributions were looking pretty normal, and the mean was getting pretty close to the coefficient values in the 20 million sample set. So, today I really wanted to focus less on the results, the technology, the statistics, and talk about, I'm really excited as a data scientist about the business decisions, the business use cases behind data science. How are we addressing those business needs with data science? And a lot of times we're strapped for resources and we just want to make an MVP. So as a data scientist, how do you hack that problem? How do you take those problems and even if you're in a large organization with a lot of resources, how do you not expend a lot of resources just to tackle an MVP? And if you're very comfortable with a linear solution like I am, I think this is a nice way to go. A couple caveats now, and Bob mentioned that I should probably touch on this. In an orthodox sense, I wasn't really doing bootstrapping, right? Because if I have 20 million samples, bootstrapping says, at least Efron's procedure says, I need to resample that 20 million times to get one bootstrap sample. So what's the point of that if I'm trying to actually reduce the number of samples I'm working with? So, a caveat here is that I'm not actually doing orthodox bootstrapping, but I think it's helpful to think about this in a bootstrapping sense. The second caveat is I did not get to dive further into this project before I came over to Health Fidelity, but how many iterations do you have to do before you're reliably getting to your Oracle coefficients? Is it, Efron, his procedures, he's saying 1,000 to 2,000 times. Maybe that's sufficient here. Maybe it varies by data set. Maybe it varies by the problem you're looking at. I don't know. So these are kind of outstanding questions in my head. And there's probably some kind of strategy you could use where, if you had 20 million samples, if you could take 10 million and do this procedure and come up with all the tuning parameters you would need to show that all your coefficients reliably converge on your Oracle coefficients, maybe that's an option. But you know, as somebody coming from academia, I'm definitely comfortable having open questions in my mind after a project like this. So with that being said, that's pretty much all I have. If people have questions or comments, I'd love to hear it.
Hey Lincoln, okay, I'll watch my chat screen as you know people typically submit questions via the via chat to me. And I did have one already. Someone had asked, how did you address, or how did you deal with the high number of dimensions?
So any of the regularized regressions are really great in a high-dimensional space, right? Because if we use ordinary least squares when we have 10,000 variables, the standard errors on the coefficients you get are going to vary wildly, right? Your standard errors are going to be huge. You can't use ordinary least squares when you have variables that are collinear. So regularized regression is great when you're in this big space because it's an unbiased way to either pare down the variables or bias the variables by shrinking them towards zero. And it's a great automated way to deal with collinearity in variables.
Okay. Another question came through. Did you test this only for lasso regression? How did coefficients compare with actual ones in your test?
Yeah, so I I only use lasso in this scenario. And then the question is how my calculated coefficients came to the coefficient from the whole 20 million sample data set.
It says, how did coefficients compare?
If that's the question, you know, my coefficients. So, like I was saying earlier, qualitatively,
like you cut out for a second there.
10 or 20 of them. Quickly. Can you hear me now?
Yes, please go ahead. Can you start over again because you had cut out there?
Hello? Yeah, sure. So, like I was saying, I did not have a chance to do a systematic, you know, review of how many coefficients were off by X amount or how many were right on within a certain margin. What I can say is that this was a quick and dirty experiment I did, and just cherry picking variables and looking at the distribution, I was pretty shocked to see how close a lot of my coefficient means came to the coefficient I got from doing the entire data set. Probably 7 out of 10 were very close to the mean, within a standard error of the mean. You know, 2 out of 10, you get some outliers, and that's why I was saying I would like to know, you know, if you up the iterations, if you tune how big your subsamples are, what does it take to reliably get to that actual coefficient 100% of the time? That's something I don't know, but I was probably within a standard error 70 or 80% of the time.
Okay, great. Another question came through. Let me just read it verbatim. Even if we use bootstrapping method, dealing with high-dimensional matrix operations takes a huge amount of time and memory. How did you deal with that? Were they problems for you? How did you adjust to it?
Yeah, I guess buy a big enough computer,
yeah.
right? So it is very intense, and there's a lot of iterations you're running through with the regularized regression. But luckily, we live in a time when you can set up a cluster on AWS, and for a pretty reasonable price, you can have some powerful machines running those computations for you. But this is the alternative to having to do a regression on 100, a last regression on 100 million samples. That's going to break down most computers pretty quickly. So I think this addresses that very question. You know, how do you do computation with a really demanding algorithm like this?
Right. I think what you just said was just the answer. What you're doing is exactly addressing that. So the solution is, and not to be funny here, but what you said, the first step is, you know, obtain as many resources as you can, meaning physical, cores, RAM, etc.
Mm-hmm.
And once you're living with that constraint, then you still, you know, it's big data. So I don't care how big it is, it's never going to be big enough. And so you do clever things like Lincoln did here, which was his subsampling method. So to answer that question, how did you deal with all this? Like Lincoln said, the answer is you do this, you do subsampling.
Yep.
Okay. And by the way, everybody is saying thanks, Lincoln, for your answers. Is there anything else someone wanted to chat through a question for Lincoln? We'll give it one more minute. Okay. I think we're good. Oh, wait, 1 minute. Lincoln, there was a request. Can you put the solution on GitHub?
No, I cannot, because I do not own the code.
Yeah, I thought that'd be your answer. This is.
I would love to maybe in the future. In the future, I'd love to put together maybe a little toy example of how this works with some sample data. And if I ever get around to that, I'll let Bob know, and he can get that out to the group.
Yeah, and the same person that said too that with those examples we could do with large data set, that'd be great. Okay, well, Lincoln, thanks a lot. And actually, as far as your toy data set and giving an example, I think it'd be great because, as you know, this is an area that I think is extremely important in the field of data science, namely the development of distributed algorithms, or how do you parallelize and distribute machine learning algorithms. I think it's a critical area for future development in data science and machine learning. I was really excited to hear that, you know, what you work on this. And, you know, we're planning perhaps an on-site, you know, to get together a session in September. Maybe we can convince Lincoln to have his example with a little more, some more details in it and do it then. But we'll see. Okay, I think that's it. Thanks, everybody.
Sure.
And Lincoln, that was excellent. It was really interesting. I especially liked it because, you know, it's kind of the theme of what this group is about. It wasn't theory. It wasn't, you know, something on a white paper. This is a real data scientist who had a problem that he had to solve for his company as a business use case. So I really appreciate what you had said, that, you know, living with your constraints, your budget, and time, to come up with a useful solution. So again, Lincoln, thank you. There's a couple more questions coming through, but I'll email them out. So again, Lincoln, thank you very much, and we'll see everybody in a couple of weeks when we're going to have Dora Tang talk about.
Yeah, no problem. Thanks for having me.
Yeah, sure. Okay. Thanks a lot, everybody. We'll see you.